trying to figure out where he can stand, you know the limits of where he can be on the system. You know he can either be here or he can be here, right? That's the limits of how far he can go. If you go there and there's still normal forces here and here, you're fine. The other way to do it is to go the other direction with it, and that is not know where he stands, but set the normal force on the opposite side to 0 and see what distance that gives you. And either one of those will work, because if you find that that distance is outside the plank, then you know that there is no distance that he can't stand, and the system will be a problem. But if you find that it's less than whatever this is right here, the 2 meters, I think that's the overhang. If you find that it's less than that, then you know that, yes, there is a place he can stand where he will cause the system to go into motion. So I believe the answer is he can stand anywhere on the plank, because I believe the limit is actually the very end. I think that's what you find out, that the place where the normal force goes to 0 is if he puts all of his weight exactly 2 meters away from the other support. I think that's the answer. It was a while since I worked this one out. Where he can't stand, it would require a downward force at that cinder block to hold it in place. And since they're not nailed down, there can't be a downward force from the cinder block. All right. Any other questions on the homework or anything I can work out at this time? Yes, sir.
Number 4.
Oh, the ladder problem. Yeah, it's a toughie, isn't it? Yeah. All right. Especially the way I worded it, which is not great. A little bit purposeful. So had you been given an actual angle and some numbers, it's actually not so terrible. But doing this as an all symbolic problem is challenging. So I'd say this one makes it, just because of that takes us up to a whole big level 3, because the algebra is going to look just atrocious. All right, so that's a bad one, but let's do it. It'll be fine. All right, so let's go through the problem from beginning to end. But I think it just asks one thing: where can he stand so it doesn't slide, right? Or what coefficient of friction is required so that he can stand someplace? All right, so we're looking for mu at the end of this problem. Shall we start with the net force portion of the problem? So I envision, based on just the net force part, that there are 5 forces acting on our person here. So starting with the ground, there's got to be an upward force. Let's make those a little bit easier to see. An upward force from the ground, normal. Come on, just stop moving. There. There's also going to have to be a frictional force, and I'm pretty sure the frictional force has to be that direction to keep the ladder from sliding outwards. Does that make sense, guys? Any questions about that? Good. So we have another force here. Weight of the ladder, straight down. Weight of the person, straight down, and normal force from the wall. In a real ladder problem, there would be another force this way. I think we're going to ignore it for this problem, but this would be the frictional force from the wall on the ladder. So there's 2 frictional forces, and they both prevent the ladder from sliding, or try to. We'll ignore that one. That's a complication that I think we can just live without for today, and we'll make it like this. All good for you guys? So let's put some labels here. Normal force from the wall, normal force from the ground, friction, and it's a static friction. What do I have? It's a mass of a person, mass of the ladder. So for right now, how about just weight of the ladder, weight of the person? Is that all good? All right, so let's set up our net force portion of the problem. And I'm going to say for the net force portion, this is the y direction, and this is the x direction, and positive based on both of those. So net force in the x direction equals 0. And I believe there's only 2 of those, friction and normal force from the wall. Any questions there? This is old school stuff, right? First semester stuff? All right. Net force in the y direction also equals 0. And I think we have a variety of forces here. Normal force from the ground minus weight of the ladder minus weight of the person. And that's it. Equals 0. Any questions about that? One more thing here that I think we probably should go ahead and bring up now. Static friction must be less than or equal to mu times the normal force from the ground. Seems to me we could bring some things together if we so wanted to. It's an inequality problem, so I kind of like preserving the inequality. You've heard me say that a lot. We could right now come up with a force relationship that we can't solve, but at least we can get, I don't know, get things kind of situated. What I mean by that is we can substitute there, and we can substitute here. So at least we're dealing with some stuff that's, you know, based on the problem, the mass of the person and stuff like that. We'll have to eliminate the normal force from the wall somewhere, but we don't know the normal force from the wall nor the frictional force, so it's one unknown versus the other. So I'm going to go with those substitutions and get normal force from wall is less than or equal to mu times, we'll say, yeah, we'll leave it like this, weight of the ladder plus the weight of the person. That's it. That's all we can get from forces, because although we may know this, we don't know that. And it's an inequality. We don't know where we are on it. All right. So let's go the other direction now. We have to come up with our torque problem. And I'm going to draw this a little different in a minute for the torque problem. But you see where theta is, right? All right. It's going to be a bit of a problem because not all these angles are theta, are they? Based on what I've drawn, this is not theta. But it is 90 minus theta. This is not theta either, but it's 90 minus theta. And this is 90 minus theta. The only one that's actually theta is this one and this one. Those are the only two that are actually theta. Everything else is 90 minus theta. Everybody good so far and understand that that's true? All righty. So 90 minus theta, 90 minus theta. Ladder. Weight. Person. Wall. Friction. Normal. Just redrawing it. And in a minute, I'm going to take away forces that we're not going to use. We have to pick a pivot point. And we were given the weight of the ladder, weight of the person. I'm trying to find mu, but we haven't been given anything else. We can come up with the normal force from the ground, which we already did. We know it's the weight of those two people, and we've already used that. Where do you want to place the pivot? I know where I want to place the pivot. We could place it anywhere we want. I think I want to know this force. That's what I want to know, because going back up here, if I figure out that force, I can use my inequality. So I don't want to eliminate that force. I want to find that force. But I don't know the frictional force. No, they're equal. I could put the pivot point right here at the ground, which is how I want to do the problem. Everybody okay with that? If I put it there, then I have fewer torques. If I put it anywhere else, I have more torques. So So get those out of the way because I don't need them. I'm going to go ahead and redraw my pivot point here. And I'm going to have 3 torques. I'm going to have the torque from the wall, the torque from the ladder, and the torque from the person. I'm indifferent to this next question, but we have to decide. What do you want to be positive? Out of the wall? I'm sorry, out of the board or into the board? All right, so out of the board is positive. So I think we have a variable to use for all of these, but we do need to be aware of some of our limitations. So let's get these limitations in here. This is theta. This is 90 minus theta. This is 90 minus theta. Now, I don't know if you know this, so I'm just going to throw it out there. Sine of 90 minus theta equals cosine theta. Do you know that that's true? Okay. I don't know if you've been taught that or not. You should show yourself this to be true. And I don't want to do this, but I feel as though it's my teacher duty to do so. Theta, 90 minus theta, opposite adjacent hypotenuse, correct? Sine of theta is opposite over hypotenuse. Cosine of 90 minus theta, what does it have to be? It has to be this side, right? Because that's adjacent to 90 minus theta. Now do you see why it's true? Okay, so we all know that now. We know, can internalize that. You don't have to. You can do the whole thing with sine of 90 minus theta in there, and your answer is technically correct. But I want you to know this. So now you know, you're smarter. All right. R sine R. Here we go. Let's start with the torque from the wall. It is the length of the ladder, capital L. Size of the force from the wall, normal force from the wall, times the sine of theta. And let's check to see if it's positive or negative by using the right-hand rule. So, torque arm distance that way. The force is upwards, so it seems like it's out of the wall. It is a positive torque. We all good? All right, positive torque. Can I just not do the right-hand rule and note that these both have to be negative because they're on the bottom side? Yes. Good. Let's see. So the next one's going to be the ladder. So that's L over 2, mass of the ladder times G times the cosine of theta, right? It's going to be the sine of 90 minus theta. So go ahead and put the cosine in there. Is that good for you guys? All right. Moving right along. They're standing at distance D, right? That's what they were using. So he's D away, mass of the person times G times the cosine of theta. These all have the sum to be equal to theta. Okay? Okay. Next part, not equal to theta. What am I saying? 0. Equal to 0. Theta. Too many theta things. So let's add them all up. L N W sine theta minus L MLG cosine theta over 2 minus D MPG. I didn't really leave myself enough room for this. Cosine theta, that's it, equals 0. That's kind of messy, sorry, but we'll work from there. I need to solve this for normal force from the wall. So let's do L NW sine theta equals L m2g cosine theta over 2 minus d mpg theta. I'm going to divide by sine, and I'm going to divide by L. Is that all okay? So, what? Oh, add, you're right. Okay. So let's divide by sine first. And now let's divide by L next. Nothing magical here. Normal force in the wall equals, I can cancel the L in the first term. So I still have the m2 g over 2 cotangent theta.
Is this supposed to be ML?
Yes, that's an L for ladder. All right, the other one, d mpg over L cotangent theta. All right. I mean, it's not pretty or anything, but it's okay. I mean, you could factor stuff out if you want, but see no reason to. But now we have normal force in terms of things that are allowed to be in our answer, right? The given information. And we've got this thing over here that we're going to have to use. I think we got to bring these things together. So I'm going to substitute there. It's going to be ugly. Here we go. MLG over 2 cotangent theta plus dmpg over L cotangent theta equals mu times MLG plus MP. Yep. Cotangent. That's what I wrote. No, I didn't. All right. Coming in. Oh, and it's less than or equal to. Coming in on the end, we're just going to solve for mu, right? We wanted mu. So, let's see. I see an ML plus MP. Is there any way I can get an ML plus MP on the other side to get it to cancel? Nope, doesn't look like it. Would have been nice, but not happening. We could do a few things to get common denominators, so it wouldn't be a completely terrible, horrible fraction, but it's going to be a pretty nasty looking piece of work at the end. So again, depending on how clean you want your algebra, if you don't get a common denominator, you'll have a compound fraction. Are you guys okay with that? All right, because we can just multiply and get common denominators, but there's nothing pretty here at all. We do have a g in every term, though, so the g will go away. Right, I can factor out a g on this side. I can factor out a g on this side, and then I can divide out the g on both sides. That's a little bit better. So m2 cotangent theta over 2 plus d mp cotangent theta over L divided by ML plus MP must be less than or equal to. Now, messy for sure. Notice that as the mass of the ladder and the mass of the person goes up, it may allow you to be okay because it's in the top and bottom. It's hard to know where it is. But clearly, the higher you stand on the ladder, because that's D, the higher you stand on the ladder here, the better you better have for friction. Because as D goes up, you need more friction. Looks like a few other things actually play a role in that too. The angle clearly plays a role. It's in both terms. It plays a pretty hefty role. And it's cotangent, so there are angles that just don't work at all. There is actual problems with this calculation if you're really trying to make a ladder and you want to make it safe. And I don't want to spend a lot of time on it. This would be what you'd have to do to get the answer. If you had numbers, you do understand it would probably work out easier because a lot of these numbers would drop down. You'd be able to put some things in earlier and not have this kind of mess. But as a symbolic problem goes, this is what you had to do. So something to think about if you are if you are really interested in like the way this would work. People don't fall off the ladders because they work like this. They fall off ladders because their mass isn't here. Their mass is up here. Do you notice that? We've made an assumption because we're working at the point of the ladder. If you're worried about the person, the torque arm to the person actually is at a different angle than the torque arm to the ladder. And so people tend to fall off ladders because they get imbalanced because of their relationship to the ladder. These forces acting on the ladder are all valid. This is how much mu you would need. But the person could fall off the ladder even if they're capable of staying on that step and not having the ladder slide out from under them. Now, please, before you guys walk out, the most common ladder that you probably have used is one that looks more like this. Have you ever used one of these ladders? You understand this might make for a somewhat complicated torque problem. Can you see why? The angles are a little weird, but it doesn't rely on friction. It relies on this thing not breaking, right? Friction doesn't have to hold the ladder in place. All right.